Hello? Is that better? Okay, awesome. All right. Hey, everyone. Oh, there's some more adjustment. Hello? Yeah, all right, that works. Hey, everyone. I'm Bikramjeet Vig. I've been at Meta for more than 2 years now, working on Velox and Presto CPP. And before that, I was working at Cloudera for 5 years. I worked on another SQL query engine called Apache Impala. So today we're going to talk about expression evaluation. We're going to start off with a quick refresher. We're just going to go through some important concepts, including an actual evaluation of a very basic expression. So that kind of sets the context for how expression evaluation works. And then you'll be able to better understand some of the optimizations that we're going to talk about later in the presentation. After that, we're going to talk about the actual optimizations. Three over here. Those are some more interesting optimizations that I thought would be worth sharing. And then finally, I would end that with a few parting thoughts about like where we are right now and what we see moving forward for this subsystem. All right, I'm going to skip through the first few slides because these have been covered very extensively in the first few session. I think Tim covered this in very high detail. So this is a very 10,000 feet view of how Presto CPP is deployed currently. It has the same Java coordinator and Presto CPP workers, which execute an optimized query plan that they get from the coordinator using Velox. Again, this graphic is used very often when talking about Velox. It basically talks about how different data engines like Presto and Spark have different components that can be put into these buckets very neatly. And Velox can replace the execution engine piece of it. So Velox is basically a vectorized execution engine that is distributed as a C++ library. And it exposes APIs and services that allow data engines like Presto and Spark over here to easily use it as an execution engine and replace it. So here we're going to talk about why expression eval is important. So expression evaluation is used in filter project and also in hash joins as like hash filtering conditions. And join filtering conditions. And here I've taken data from one of our shadow clusters. So this data basically represents CPU time taken by each operator. And the shadow cluster internally is a cluster that runs Presto CPP and then randomly picks queries from an actual production Presto Java clusters to run them. So here you can see that actually, I would like to also point you to which operators are kind of important over here. So on the left-hand side, we see Presto Java. You see that it has a filter project operator and also the scan filter and project operator. So we have similar operators both in Velox as compared to Presto Java. Like a small difference over here is that the scan filter and project operator is fused as well on the Presto Java side. But roughly, you can see that both of them added together comes around 60%. And on the Velox side, we have the filter project completely separate. So you can see if you add all of these things again up, it's going to be roughly around 60%. But the filter project specifically is 30%. Now, keep that in mind, like this distribution is not going to be the exact same for every workload. But for this day specifically, for this shadow cluster, this is what we got. So this is kind of like to illustrate that filter project is a non-trivial part of where CPU time goes, and it deserves the amount of attention that we have given it to optimize its execution. So I talked about that Velox is a vectorized query engine. So to do that, it actually stores data in a columnar format in memory. And here, this is a quick comparison of row versus columnar formats, which are two different formats that data engines typically use. And here you can see for a columnar format, it basically takes all the values in a particular column and then puts them in a one contiguous block of memory, and then puts these columns side by side in memory again. Now, this is kind of important because typical file formats like park and ORC, which are very widely used, also store data in this format. And they also have some optimizations built on top of them where they use like different encodings to more efficiently store data, like dictionary encoding, constant encoding. And then what we do in Velox is we preserve this encoding when we read them from file. And then this gets preserved through the execution pipeline, and we build our evaluation engine on top of these, so we can leverage some of these encodings ourselves. So let's quickly go through how an expression is evaluated in Velox. This is a TPCH query 14 basic query. I've marked the expressions in green. You can see they've been used for projection on the top and then as join filters at the bottom. Now this gets converted, we're going to focus on one of these. We'll take the one in yellow over here, and this gets converted into an expression tree. And now you might be familiar with evaluating expressions using expression tree from your basic computer science classes. So this is exactly how we do it over here as well. Now the expression eval engine in Velox takes three things as inputs: the expression tree itself, the input data, and over here you see it references three different columns. And then there's another third thing which is called the selectivity vector. So this is a very basic concept. So selectivity vector is basically a vector of booleans which tells the expression which rows are active, and it only needs to evaluate the result for those particular rows. Now it's going to be apparent why this is required in the upcoming slides once we actually go through an actual evaluation. So in this graphic, the green box represents the selectivity vector we talked about earlier, and then the white box are actually the values, and it's given in a columnar format over here. So we start the execution. The p-type is a column reference, and all the rows have been activated over here. It returns the values for all of these rows. It goes to the constant one, returns a constant value for all of these rows again. And then the like expression is executed. Now you see over here, only the third row comes out as true, and all of them are marked as 0. So since this is a case expression, the first subtree is basically the condition. The next one is what would be evaluated for all the rows that passed the condition, and then the third one is for all the rows that did not. So when we go to the second subtree, we would only mark the third row that passed this condition as activated, and it would only be evaluated for that particular row. So you see in the green box, this is exactly what we're doing, and we only need the result for one of these rows. So again, it goes forward, calculates the value, and then it goes to the third subtree, and now it needs the values for the rows that did not pass, which are those three rows, and it's just going to return 0 because that's the constant required. And finally, the case expression would collate all these values and then return the result. Now, before we go further, let's take a little bit deeper look into how vectors are represented in memory in Velox. And this is going to be important when we talk about these optimizations. So let's take a logical table that has two columns, input integer column and varchar column at the top over here. Can you guys see my mouse? Yeah, okay. All right, yeah, so let's say the integer column is stored as a flat vector. So the flat vector is very simple. It's very similar to a standard vector. It has all the values in a contiguous block of memory that we call the values buffer. But it also has another buffer called the nulls buffer, which is again a vector of booleans that tells whether a particular row index is null or not. So for example, if you take row index 2 over here, you see that the values just has some garbage value over there, but the nulls is marked as 0, which is an indicator that this particular row index is null. Now, if you go to the dictionary encoded vector, so remember I talked about park and ORC using a different kind of encodings. This is one of the examples. So a dictionary encoded vector basically has a set of unique values underneath, which in Velox are stored as a flat vector that we discussed earlier. So in this case, you see there are like 5 unique values. And then what it does, it creates a set of indices on top of it. So it's basically a buffer, a vector of indices on top of it. And it has a value for each row index, and it tells what the actual value for that row index should be. So for example, let's take index 2, for example. it has the dictionary index 0 over here, and when you map it to the underlying vector, you get the value red. Now there's also a nulls buffer attached to here over here, but for simplicity's sake, I've just removed it for now. All right, so these are a couple of optimizations that we employ in expression evaluation. There are more, but these are the ones that I could come up with the top of my head. And we are only going to be talking about the top 3 because we're very short on time. So hope you enjoy those. All right, let's talk about dictionary peeling. Now we're going to get straight into the dictionary encoded thing over here because we just saw how these are kind of set in memory. So let's take a very simple expression upper that uses a column reference called color call. Now this column is actually stored as dictionary vector that you see on the left hand side. And before we execute it, we check this column, it's dictionary encoded. What we do, we peel away this encoding, the set of indices that we talked about earlier. We peel that away. So what that means is it's going to look like this. So what happens is it peels away these indices, stores them, and then passes the underlying smaller set of unique values to be evaluated. This, in practice, greatly reduces the amount of values you actually need to evaluate. And then this gets piped into this expression, and then the upper only needs to be evaluated for these 6 unique values. And once you have that result, you're going to wrap it back with this peel and then get a value for each row index. And it's going to kind of look like this. So you see, you only evaluated for a small subset of rows that you actually needed, and then you can get the result for all of them. All right, so one thing to note over here is if you have only a few rows that are activated, which is marked by the selectivity vector you see on the left, so a couple of them have actually been deactivated, you need to make sure that you also translate the selectivity vector when you peel this. So if you remember, we talked that when you're actually evaluating an expression, you need the selectivity vector as well. So you need to tell the expression which rows in the underlying set of unique values are to be evaluated. So in this case, when we peel it away and we translate this selectivity vector, it's kind of going to look like this. So you notice some of the rows actually did not get touched at all. So you can just deactivate them and only evaluate the ones that were actually used in the top level dictionary vector. Another thing to take care of is when you decide when to peel. So ideally, we would want to peel as higher up in the expression tree so that the rest of the subtrees should be evaluating on the smaller subset as well. But you can only peel when all of the column references for that particular subtree have the exact same dictionary. So in this case, you see when you are at the case expression, it has 3 column references. P type is flat, but the other 2 are dictionary encoded, and fortunately they have the exact same dictionary. However, you can't really peel over here because there's no way you can successfully peel and form an input that only has these 3 rows. So you can't really translate the selectivity vector, and you can't be really uniform in specifying how these need to be evaluated. It's a similar case if you have different dictionaries, because then different rows have different indices, they map to different rows. So you can't really translate the selectivity vector in this case as well. So you have to also skip. Now, fortunately, when you go down to the multiply expression in this case, now the field references are only 2. So you now attempt peeling again, and you see that the references have the exact same dictionary. So this is the perfect condition where you can actually peel both of them and then also trans the selectivity vector like we discussed before. All right, that's about peeling. The other thing we do is lazy materialization. Now, I'm pretty sure you guys are familiar with the concept of lazy materialization, and we employ this in Velox using a concept called lazy vectors. So lazy vectors is basically kind of like a pseudo vector that doesn't really have any data right now, but the data is only loaded or materialized whenever it needs to be used the first time. So this has a bunch of usefulness. It can, by deferring these computation values, we can save on memory. And also, when we actually need to use the data, it's possible that we actually don't need to load all of the rows as well. And this saves you a lot of computation in memory, especially for like large complex types. So let's take an example of this in works. Now in this expression, we have an AND conjunct, and it has 3 different conditions. And the columns over here are C0, C1, and C2. And in this specifically, C2 is the lazy vector. All of the other 2 have already been loaded. So you see, again, it also has the same legend. Like the green box represents the selectivity vector, and the white box represents the actual values in the vector. So you execute the first condition over here. There are only 2 rows that pass this condition, the second and third. You get to the next one, only the third row now passes this condition. And then when you get to the third condition, you only need the value for the third row. So you only load the third row in the lazy vector. Now the best case would be that you get all false before, and then you don't need to evaluate this subtree at all. So you don't need to load anything at all over here. The biggest caveat over here is that since we serialize this on first use, we need to know exactly the set of rows that would ever be touched during the lifetime of that lazy vector. Now what I mean by this, take a simple case, for example. Take array constructor. Now the array constructor is a non-null propagating expression. What that means is if it gets a null as an input from one of its input, it's not just going to return a null. It'll just use that null as one of the values in the array that it returns. However, the child expression over here, the plus function, actually is a null propagating expression. So when it gets null from its first child, it's the C0 column over here, it knows it's just going to return null. So you don't really need to evaluate C1 for that particular row in this case. So we can skip it when we load C1, and we don't load the row index 3 over here. However, when we go to the next child in array constructor, we actually end up needing that particular row. So if you would not have loaded this in the first instance, you would be in all sorts of trouble. So now, one way of handling these cases is when you're actually going through the expression tree, you identify cases where you know for sure that a set of rows is going to reduce, and for cases where you're not really sure if they're going to reduce or not. Now, when we saw in the very basic AND expression case, we knew for sure that it's going to reduce, so we reduce the set of rows in that case. However, over here, you have an AND expression under an OR expression. And this is one of the cases where you don't know if the set is going to reduce once you go down. So what we're going to do is, in these cases, we're going to fix the set of rows to the set that the OR expression got as input. Now in this case, all of them are set to true, but if there were fewer, we would have set it at that particular selectivity vector itself. Now let's see how this helps us. Now, when we transition from the OR to the AND expression, we set it to this set of rows, and now we start evaluating the conditions in the AND expression. So you see for the first one, 2 of the rows get filtered out. In the next one, C1 was the lazy vector, but now instead of loading just the first and the fourth row, we're going to load all of them because that was the set that we fixed it at the top. Now when we get to the next AND expression, you see when we need to use the C1 column again, we actually needed that row. So it's a good thing that we identified this and loaded it in the first place so we don't run into issues. Now let's go to the next one, common sub-expression. Now this is very simple to understand. Presto Java also does that, so you might be familiar with it. The first thing that we do over here is when we are parsing this expression tree, you identify all the subtrees or the sub-expressions that are the exact same. And then on every instance, on the first instance, when you encounter this, you would cache the results and you would cache the rows that were evaluated for this particular sub-expression. And on the second instance, For the rows that are required for the second instance, you'll check against these cache set of rows. And if you have the result for them, you're just going to copy them from the cache. Now, fortunately for this case, all of the rows were evaluated and we needed all of the rows. So we're just going to copy them and return them. Now, let's take a case where the rows are not exactly the same. Now, in this case, in the first instance, you see that only 2 of the rows needed to be evaluated. So only 2 of them were cached. But in the next instance, the first and the fourth one was required. So now it's going to compare against the set of cached rows, and then it's going to split up into a set of rows that it can copy from the cache, and the set it needs to evaluate it. Now, in most cases, this set that it needs to evaluate is going to be much smaller than initially that it would have evaluated again and again. And then those are the only ones that now need to be evaluated, and those itself would also again be added to the cache. And then that's what exactly that it does. So it copies it from the cache and the ones that it evaluated, and then returns the result. All right, final parting thoughts. So currently, we're very happy with the implementation that the optimizations that we have right now in the core expression eval engine. It's stable, and what I mean by that is the performance is good, it's bug-free. So we don't really have any incentive currently to go ahead and tinker with it a bit more. And one of the other reasons why we don't have that is because we've been focusing a lot on productionizing through Presto CPP internally. And I'm sure you looked at some of the numbers from Sergey's presentation this morning. So we've been focusing a lot on correctness. And because it's stable, it allowed us to focus on other things like correctness in this case. So we've been focusing a lot on like testing around correctness and also improving our fuzz testing framework. And for the future, the first thing that I mentioned over here is like there's always scope for improvement, right? So we have seen like 1 or 2 conditions where we can actually further optimize, further fine-tune these optimizations, specifically for some use cases that employ complexities like arrays and maps. But apart from that, we are also eventually going to be running Velox with Spark, and then that would expose many different types of workloads to this system. And we're hopeful that we'll see even more points where we can optimize in the expression eval engine, or maybe come up with new optimizations altogether. So, all right, that was all. I hope I'm right on time. If you have any questions, you can go ahead, or if you want to reach out to me, there's my email address. Yeah.
Might be off topic, so just let me know if it's off topic. But I was just curious, like it looks like you have a future roadmap for further optimizations. How do you know how to prioritize them? Like, how do you know how effective they might be? And and do you measure the effectiveness after you've implemented it, like on production workloads or whatever?
Yeah, so let me set that in context a little bit. So when we started to go into production, we already had some basic set of these optimizations implemented. But when we were going through this whole phase, when we were going to production, we saw some places where we were actually slower than Presto Java. And in some cases, it was actually pretty bad. Like for example, off the top of my head, I remember there was this one case where we did not have any common sub-expression reuse being used because we were disabling it whenever we did dictionary peeling. And in that case, one of these queries was actually going more than an hour, so it didn't even run, whereas Presto Java was running it in 20 minutes. So we identified this case, we identified this deficiency, went ahead and implemented a way to actually use both of these together. And it's actually very difficult to make sure that all of these optimizations work well together. They can result in many complex bugs, which we don't have time to talk about today. But once we did that, we actually saw that the query finished within 3 minutes. So it was a huge speed up. So because these optimizations are very workload dependent, they're very dependent on the query shape, they're also dependent on the data. You can't really have numbers like on a wider set of queries. For some, they are like extremely fast, like in this case that I shared. For some, they don't really matter as much because they don't end up being used at all. So traditionally from when I joined, I've seen like whenever we see these deficiencies, we've just went ahead and like fixed them. That's why I said like right now we are looking at fine tuning whenever we see opportunities. But I'm hoping when we actually get to the point where we have like Spark workloads as well, we might be able to find more places where we can optimize them even further. And not just Spark, like even for AI ML workloads, their usage patterns are also very different because they have like extremely huge maps and arrays. So there are opportunities that over there we can also optimize as well. Do we have any other questions?
So I have a question. So for expression tree, with many and ors, so basically, do you evaluate sequentially, or you can dynamically change the order because of like selectivity, right? You already show that we can do early termination, something like that.
Mm-hmm.
So do you evaluate expression like exactly it written, or
Uh-huh.
you can switch the order how it get
So right now we don't switch the order of ands and ors. I think that is something that the optimizer above Velox can do, like maybe in Presto. But once you have that plan, you can do something like you can squeeze, like if you have an and under an and under an and, you can just like squeeze them in a single and. So you can do that. One other thing that we do is what we call adaptability. It's like say you have like multiple conditions under a single and. We keep track of which condition was the most effective for weeding things out, and we actually switch them on the fly between different input batches. Yeah.
Another question, it might be slightly off topic, but like thinking about like special form expressions, some of them short circuit. Do you like does that do you like supposing one of them results in an error? Do you kind of like do you eagerly evaluate the error, or do you like is there any special smarts to kind of like make the error lazy because of that short circuiting property? Like meaning like and x, like and true and x, and then x is some sort of condition which would divide by zero or something like that.
I don't think there's any adaptability in errors similar to what we discussed in ants. Yeah, those are like data dependent things where you could probably add adaptability, but errors might be a bit more I don't know, difficult to predict, I guess. But yeah, right now I don't think there's anything like that. I mean, it's easier to do it in like conditions, maybe and condition. We can maybe do something like that for like the and conjuncts, but I don't know if similar kinds of adaptability can be used for like subtrees in specific. Right. Done. Okay. All right. Thank you, everyone.